everyone, I'm Matt Ford, and welcome to the Good Trouble Show. There are many universal truths in the world that you can bank on, such as the sky is blue, or the earth is round, or that you will always pay taxes, or the Pentagon, the CIA, the NSA, the Department of Energy, all in coordination with the C-suite executives of just about every major defense and aerospace contractors are colluding to lie to Congress and the American public on UAPs, otherwise known as UFOs. Now, one mechanism used in this illegal collusion is by hiding radar data of UAPs from Congress by overclassifying that information. These gatekeepers use overclassification to hide what they know about UAPs and what they know about the literal thousands of drones operating with impunity over our military installations and off our coasts above our carrier strike groups, endangering our military pilots. The Pentagon, the IC, and the defense contractors do not want Congress to know that these drones harassing our military are actually UAPs. They are not from a foreign adversary. They are not from China. They are not from Russia. They are from our friends out there, and they will lie tooth and nail to our congressional lawmakers to hide this reality. So, the question is, how do you defeat a Pentagon intelligence and military-industrial complex hell-bent on covering up this and protecting their bank accounts? You put in the hands of the average American citizen scientific instruments at an affordable cost that will display in real time and with zero doubt what is flying in our skies. Today, we have a physicist and engineer who will reveal for the first time his product that will finally expose the decades of literal lies that our government has been telling us and Congress regarding UAP. But first, please hit the subscribe and thumbs up buttons on YouTube. Leave a comment and let us know what you think about this episode. You can also find us on X at Good Trouble Show and everywhere else at The Good Trouble Show. You can also find us wherever you enjoy your podcasts. Search for The Good Trouble Show with Matt Ford. And as always, if you would like to chip in to help keep the lights on, you can become a Patreon member of The Good Trouble Show by going to www.patreon.com/The Good Trouble Show. Sign up and you can support our work. We would certainly appreciate it. Our guest is an inventor with a master's degree, or two master's degrees in both physics and electrical engineering, creating instrumentation and ground-based and airborne-based radar systems, that's a mouthful there, used today by NASA and NOAA. He made the mobile Doppler weather radar for tornado chasing trucks, which is now the industry standard for weather research worldwide. And if that's not enough, he invented wireless charging technology named by Time magazine as one of the best inventions of 2007. His interest in UAP led him to the Galileo Project as a researcher. Please welcome Mitch Randall. Mitch, how are you, sir?
Very good. Thanks for having me on. How are you doing?
I'm doing great. Glad to have you here. So that is quite a resume. Is there anything that I missed in your professional background?
I mean, I'm a toy inventor also. There's toys on the market. I'm just an entrepreneur, and I love to tinker with stuff. All the radars that you mentioned, those are weather radars. So that's where my interest or my profession has been. Yeah.
And we're going to dig into radar. I know that's like what you use to look at the weather and what the cops use when they're trying to bust you for speeding, but that's about it. So we're going to dig into the technical aspects of radar. Hopefully, explain it to someone like myself that does not have much of a technical background. But this is really great. As you and I spoke about when we met at Contact in the Desert back in the summer, one of the challenges with this whole UAP issue is the government, in particular the Pentagon, NSA, CIA, they have reams upon reams of radar data of UAP, of both the prosaic stuff, which, could be Chinese balloons, etc., but they also have tons and tons of radar data on UAP of non non-human intelligence, vehicles created by non-human intelligence, that they are not sharing this data with Congress, let alone the American public. So your product is going to come to the rescue. We're going to talk about the history of it, but first, I want to know, is like the whole radar thing, has this been kind of your primary career focus?
More or less. I mean, I'm working at the National Center for Atmospheric Research. My job was to come up with instrumentation that scientists would be able to utilize, to solve, they don't know what's possible. So it takes an engineer and physicist to figure out here's what we can do with technology. So we would develop instruments, and then we would say to the scientists, the meteorologists, so we'd say, could this be useful for you? And they go, whoa, yeah, that'd be great. So I'm really used to that kind of paradigm where we're kind of leading, the scientists aren't the ones who define the instrumentation. It's really the engineering and the technology defines where you can go with the instrumentation. So that's exactly what I'm doing here.
Now, as I mentioned, you developed the mobile Doppler radar system used in tornado chasing. And one of the things I love to watch on YouTube are these storm chaser videos of all these guys chasing tornadoes. What's your scariest tornado experience?
It's scary for the wrong reason. It was a shakedown test of what was called Dow 1, the very first Doppler on wheels radar truck. And I had taken a bunch of pictures, but then this tornado started to form, and I took a lot of pictures of that, and it was like such an exciting experience for me. But I realized that I had taken the film roll out to change it. I didn't put a new film roll back in. So that was that was where all the fear came from.
Yeah, that sounds like something I would do. Go on ahead.
It wasn't. They're actually pretty safe. They know what they're doing, and they're looking at satellite data, whatever. So they're not getting themselves in harm's way. The amateur, it might be a little different with the amateur storm chasers, but the pro storm chasers, the professors and grad students that go out there, they know what they're doing.
So Mitch, how did you become interested in the UAP topic?
Oh, that goes way back. So I'm no youngster. It was decades ago. Just interested, but I went through these cycles just like we're seeing today, where, wow, it seems like something's happening, and then kind of nothing for a while. Then, looks like something's happening. That's just part of this field and how it works. But about in around 2000 or so, I saw Peter Davenport from the National UFO Reporting Center. He had published a paper about bistatic radar, which is what we're talking about today. It's called either passive radar, sometimes they call it bistatic radar, sometimes multistatic radar. So he wrote a paper about it, and I was thinking, wow, this is great, because I made a bistatic weather radar just a few years prior to that, and went through all the ins and outs of figuring out how to make that work and publishing papers on that, etc. So I contacted him, and we began a relationship back in 2000.
That's fantastic. So this technology, and again, we'll dig into the details here in a bit. This isn't something like brand new you've invented. This is something that has been around.
Oh, for sure. In fact, Peter Davenport, he wrote a paper in 2004 for a presentation at MUFON, and it's really complete. He goes through kind of the history of bistatic radar. It's pretty darn good, where he shows some of the very first uses were back in World War II, where they were using, if the enemy would come over where it would normally be out of range of FM radio, it would pick up, or AM radio probably at the time, it would reflect that off, and then in their receivers, they could see that something must have come into the sky. So they were using bistatic radar back in World War II. But it goes on, one of the most sophisticated systems out there right now is, it's been replaced. That's why I kind of stuttered a little bit, but
sure.
Up to a little while ago, it's called the Fence, and they have receivers all across the nation, like 8 receivers along a certain latitude all across the nation, looking up, and then they have a transmitter, and they can see objects in space up as small as 10 centimeters in diameter out to 27,000 kilometers.
Wow. So certainly they would be able to detect UAP coming in and out of the atmosphere with something like that.
Oh, there is no doubt about that. And but you have to also look at the specs too, because even though you can, your radar has to be really tuned to the job you're trying to do. So I don't know where, for example, what kind of velocities they can measure. A lot of times with the radars, for example, with storm chasing trucks is a good example. The wind velocities can be 300 miles an hour. So unfortunately, the radars aren't capable of measuring 300 miles an hour. They have to go through a little process in post-processing to try to estimate which range they're in, because it starts to roll over. It starts to alias itself. But anyway, I'm sure that system is pretty awesome and can see a lot of blips up there. There's no doubt about that.
And I understand you were a researcher at the Galileo project. Is that correct?
Yeah, back in 2021. Well, for one thing, just to finish up with the Peter Davenport part of that, at the time, the hardware was kind of a pain, and I would only be doing this as a volunteer at the time. So it kind of tapered off. I didn't really build anything for Peter back in the day, in the 2000s. But, things changed quite a bit in like 2012 or so. They came out with this little receiver for digital TV that's just a dongle you can plug in your computer. And then hackers figured out how to get the data out of that thing. So it's basically a receiver that you could get raw sample data from RF spectrum sampled and into your computer. So I got interested in it again. And then in 2021, I saw Avi Loeb announce the start of the Galileo project. And I saw that his plan was to put 50 telescopes out there. That's what he announced back in 2021. And I thought to myself, well, you're not going to be able to find a UFO with a telescope. It has a very narrow beam. So I don't know how you can do that. So I contacted them because I knew they're going to need some kind of detection system that can, figure out where to point their telescopes.
Sure.
So I did contact Avi actually right after his press release. I mean, minutes after his press release, and he had that live stream where he's announcing and talking about what they're going to do for the Galileo project. And I think Avi wins an award for the most amazing fast email responder on Earth. Because just within minutes he replied to me. But later, with my history with the project, I realize everybody sees that. He's an amazing email answerer.
Now, I mentioned earlier that one of the limitations with relying on the government for data is that they are just simply not going to share it. And especially with the radar end of things or other sensor systems, classified sensor systems. Now, I know other folks have come up with sort of like electro-optical UAP detection systems. What are the limitations of those systems?
I mean, notice that the government's happy to give you any data as long as it's not radar data, as long as you can't actually draw a conclusion from it.
Right.
And one of the problems with any kind of image, whether it's an infrared image or a camera image, the problem is it's two-dimensional. You don't know that third dimension. When you don't know that third dimension, was it a bug that just went, in front of the camera, or is it 100 miles away and it went, lightning speed? So without that depth information, and you can see this too, if you're on UFO Twitter and you're watching the debate about, the gimbal video and the go fast video, et cetera, you realize, and also the Aguadera or Aguadilla, whatever how you pronounce that, the problem is they don't know how far away it is. So they can't draw the conclusions. They can try to estimate, they can argue about it, but you're never going to get a definitive result. And you're certainly not going to get a scientific result, without bringing in some kind of other assumptions. So that's the limitation. That's the big one.
That totally makes sense. So why don't you walk us through this technology, and then after kind of like talking about the history of it and other people that have used this in the military, then we're going to do a live demo of what you have developed so far.
Yeah, that sounds great. Let's see, if you could pick up the screen, I have a little picture up here.
Great.
So this is what I proposed for the Galileo project. This is actually one image from the paper that was published in the Journal of Astronomical Instrumentation that the Galileo project put together several papers, and this is the one I wrote for that special issue. But this describes what I was trying to do with the Galileo project. What you have is the idea is that you have receivers around, but you have transmitters, and they already exist. You have an FM transmitter that's already blasting power out into the atmosphere. In fact, way more power than a typical weather radar or even than a typical military radar. Because what really matters to sensitivity is average power, and FM transmitters put out like 100,000 watts average power, effective average power, whereas a typical radar, like the weather radars I use, more like 1,000 watts.
Wow.
I'm sorry, more like, 1,000 watts. So it's 100 times more power. And you can really do a lot with that extra signal power. But here's if you can see my cursor,
Sure.
you have an FM transmitter. It's sending signals everywhere, but some of it's going to go and hit this airplane. By the way, in this paper, I decided not to have my little UFO icon. I put in an airplane,
Okay.
just not to raise everybody's hair on the back of their neck.
Right.
But it's going to reflect off this airplane, come back to just some receiver. Okay, that's all fine. But also, there's a direct signal that also gets to that receiver. So now you have two signals that are coming to the receiver. One of them is a replica of what the transmitter transmitted. The other one got delayed by this path length here.
Okay.
Out to the radar and out to the reflector and back to the system. So the difference in those two path lengths, you can figure that out by doing a correlation process. And this is, by the way, I didn't invent this. This is passive radar technology. One of the best papers on it is by Holland in 2005. I have that paper. We can look at that.
Sure. Yes.
Should I bring it up now?
Yeah, go for it. Why not?
Well, let me just finish for a second. You're just giving the kind of the big picture here. When the airplane moves, of course, this range changes, obviously. And here's what radar is. Radar is radio detection and ranging. That's what the acronym stands for. So not only can you detect something, but you can actually get the range of it. And that's done by signal processing that's in the receiver. And by the way, there is another way to do it. I won't spend much time on it because it's kind of a niche case. But you don't have to use the direct signal. You can also use a recorded signal to recover that range and detection with the system that's shown on the right here. But this is kind of the primary system and the one that's also talked about in the Holland paper.
Okay.
Let me pull that up if I could. Yeah, here's the idea. So when the system is running and you're getting these echoes, you can't exactly locate where that airplane is. All you know is that delay difference.
Okay.
Okay, on this picture you're looking at right here, you can just plot that in terms of on this axis that goes from left to right is range or delay, really. And then on this other axis is Doppler. And what the Doppler is as that range changes, the frequency, the phase of the signal changes, and a moving phase is a frequency. So if something's moving away from you fast, you can count those phases and figure out a Doppler shift from it. And if something's moving towards you, you're getting more waves towards you, and you're getting a phase shift in the opposite direction. So you can see that Doppler, and you can tell if the object is increasing in delay or decreasing in delay. So that's this vertical axis here. So I hope that's not too technical or put you to sleep or whatever.
No, that's good.
That's what the two axes here are doing for you. So, you can have an air, and then, by the way, in this example, these, I might have this backwards, but the tracks, I think, are from FAA data, and the squares are what the radar detected, the passive radar detected. So you can see that they line up.
Yes.
So this is FAA. Actually, it's not FAA either, by the way, because this was all done in Europe. It's whatever their European agency is called. But they have the data for what, the actual locations of the airplanes.
Okay.
And you can put that onto this graph. You can't go the other way. You can't say, oh, I have a dot on this graph, so therefore I know where the airplane is. But if you do know where the airplane is and its velocity, you can plot it on this picture. if that makes sense.
Yes.
Yeah.
Yeah, it
And
totally
this is,
does.
by the way, just with one receiver. This is what one receiver will do. So that's the work by Holland. And by the way, I'll just scroll up here a little bit, just kind of run it by you. But it goes into great detail about exactly how you do this. So you can, if you like reading papers and then writing code to match, you can go through this and figure out how to do it. So, you know, I'm already pretty versed on bistatic radar, but I definitely got something out of this paper, and I duplicated these results for the Galileo project.
Fantastic. And what other defense contractors have used this? You showed something that I think was from Lockheed Martin.
Yeah, let me pull that up. So again, this isn't we're not reinventing the wheel here. The wheel's been invented, and all we're doing is repurposing it for this specific use. And I'll tell you why later or now. I mean, basically, it's cheap. I could make this is just an FM receiver that you could purchase, and nowadays the processing power is cheap enough that this thing could be, let's say, $500.
Wow.
Which if somebody could buy one of these and put it on their, you know, set it up like how you would set up a printer, you know, it'd be just a box that you plug in your internet cable and you plug a wire for the antenna, and boom, it starts receiving these signals. So I mean, that's the idea here, is you can make a cheap system out of this because it's just receive only, and it relies then on digital signal processing. But let me show you there's some really strategic reasons why the military would want to have this. And so Lockheed Martin developed this system, I think in the late 90s. But this is more or less exactly what we're talking about. This was a few years before Holland published his paper. And by the way, I'll just give you a little background.
Sure.
Holland did that work. He works, he's somebody at the NATO SHAPE headquarters. So he works there, and one of their ideas was, can this be used to replace all of our air surveillance radars for, you know, air traffic control? So they were looking at this from a very serious perspective of whether this is up to the task. I actually don't know. I mean, I don't think they're using it now for that, but I mean, his results are very impressive.
Wow.
Just like what I'll show you a little bit here, because we're going to take the same kind of data while we're on the call.
Great.
But this system by Lockheed Martin is pretty much got the same elements that we're talking about. It's some kind of, this box that's on this big trailer is now going to be a little box that goes on your desk, because now it's 2024 and not 1998. Right. And then there'll be some antenna on your roof. And then it'll be able to receive the data. So here they're pretty much showing you the same, you know, they're showing off their system, and basically the same thing Holland proved. Hey, there's radar tracks that match the aircraft tracks, so we know it's working. But this is a little blurb, but you can find this on the internet. That's where I picked this up. So the idea, another really important thing for the military is nobody can detect that you're looking. So you're not transmitting anything. So you're not any kind of target. Nobody knows that you're doing this. You're just sitting there receiving signals that happen to fall on your antenna.
Gotcha. Wow. Yeah. So this thing is, it is clearly proven technology. If Lockheed Martin developed it, and of course, I think everyone here pretty much knows Lockheed Martin is very heavily involved in UAP crash retrieval and other things that they are hiding from Congress in a very big way. So I guess my question is, how do we know that this system would pick up UAP?
I mean, it's a great question. I've thought a lot about this, and it's fun because, for one thing, we know that UFOs get picked up on radars because people have said that. The whole Tic Tac thing was all about, they were observing these things for a week or weeks prior to the big encounter that they had. They saw it on radar. They actually thought there was something wrong with the radar because these blips weren't moving like anything should move. So we know that radar picks up something, but there's a flip side of it. We get radar, we get UFO reports. We don't have access, by the way, to military radar data.
Right.
But people are out there making reports. But just imagine they're only seeing stuff that either it's a daylight sighting, right? And you can go outside right now and look for airplanes, see if you can see 50 airplanes, because my radar can see 50 airplanes, but you can't see 50 airplanes up there. You can maybe see two at a time or whatever, because they become dots and they become really hard to see. But also, people report UFOs at nighttime, but those are the ones that glow. We don't know that every UAP glows or UFO glows. That just happen to be that the ones that do are the ones that get reported. For all we know, maybe every night there's 50 UFOs go over your head that you would never see. Yeah.
Wow.
So maybe the military knows that, but they're not telling us.
Yeah, they don't like to tell us much of anything. If they're not being truthful with Congress, and we know that the Pentagon has been lying through their teeth to our lawmakers for literally decades, and they continue to do so. They sure as hell are not going to be honest with the American people. And I think this is what is so fantastic about this is these are the tools that will put the ability to collect scientific data on UAP in the hands of Americans, let alone people worldwide. Because you truly think that this will be an affordable thing that can be deployed on a broad level.
Well, yeah, let's talk about that for a second. So there's one way to develop instrumentation. I think the Galileo project is going down this path, where you have a suite of instruments, RF emission detector, optical infrared, some kind of telescope, zoom kind of thing. You can put together a bunch of instruments for great cost, typically, because we want them to be scientific grade instruments that are gathering data that's calibrated, et cetera, right? But then you put those, let's say, 10 places, and then you sit back and wait for a UFO to fly over one of those 10 places. So that's one approach. And by the way, I'm really familiar with that approach because the weather research community has been interested in tornadoes forever.
Right.
But how often do you think a tornado flew right by one of their, research radars? It basically, as far as I know, has never happened. I don't have any knowledge of that ever happening. What had to be done was to find out a way to get to the tornadoes. So that's how the Doppler on wheels started, is because we realized if great that you have a scientific instrument, but if it's nowhere near the phenomena you're trying to study, who cares, right?
Right.
So the idea here is, I took it to the limit. So not 10 sites, but how about 10,000 sites? If we had 10,000 sites, we would have multiple radar coverage of every object that is over the continental United States. Now, there's no way that you could hire a staff to run that system. So this is not a scientific endeavor, like NASA would do or something like that. This has to be citizen science. So that's where I've taken it, and that's my concept that I'm pushing forward. Is this needs to be turned into a consumer product that you can buy, Matt, or anybody else, and just install it just like you would install a printer. Like, you don't need to be a scientist. You don't need to adjust anything. You just plug it in and it starts collecting this data. But what we do need is a lot of people have to do that. Because otherwise we're going to have low statistics. We want high statistics.
Right. So in addition to having this sort of array of radar detectors, essentially these passive detectors, does that end up just becoming one giant phased array radar system?
Oh yeah, I didn't get that far in this one picture. Of course, all the data that's collected from these receivers would all go through a pyramidal server network. So in other words, your local data would go to a server, but then that would be combined with kind of a more broad server, and that would all end up at some central server where that data then can be combined and turned into triangulated XYZ coordinates and XYZ velocity coordinates that can just be put on a map. So I wonder if I have I don't have right in front of me an example of what that map would look like. But, you can imagine just a map of the United States or a zoomed in part of your state or over your house or whatever that just shows if there's anything anomalous that happens to be flying over. Shows its velocity and its acceleration it experienced. And, that kind of thing. I mean, I've presented this to people who said, well, in one case, I said, you might be able to prove UFOs are real twice a week.
Wow.
And the guy said, oh, no, I don't think so. I mean, maybe twice a month. I'm like, okay.
Whatever. Yeah, still.
All right, sure. I'll give you that.
Yeah, absolutely. And I actually spoke to someone, an expert in this area, and asked this individual if this system would detect pickup UAP, and this person said, absolutely, it does work. It does detect UAP, full stop. The concept is so simple, you can't fool it. And one of the things that I understand as well is that, as you mentioned, this will help display vehicles that are exhibiting one of the 5 observables in terms of instantaneous acceleration, hypersonic velocity, correct?
That's such a great point. The 5 observables, it's a great list, but if you really dig into it, what's really important, let's say hypersonic velocity. If you see something that's hypersonic velocity, that does not mean that it's a UFO. It doesn't mean it's from space, a space alien, right? You can't make that leap because we can make something that goes hypersonic velocity. You can't, I think stealth is one of them. So if there's something up there that's stealth, well, we make stealth things. And even if let's say it looks like a flying saucer, so there's no control surfaces or whatever. Well, actually, we have that technology. It's called a balloon. You can make a balloon that looks like a UFO, and we could take a picture of it. That does not prove that it's from, space. So the only one observable that really matters, that's really basically undebunkable, is instantaneous acceleration, which is what this whole system is designed to detect.
Wow.
So instantaneous acceleration is, let's say an object is stationary in the sky, like a balloon might be, but then suddenly takes off at Mach 1, in the blink of an eye. Okay, well, not only is that unusual, but if I gave a group of scientists $10 million to fake that, they can't fake it. We do not know how to do that. There's a lot of stuff that we can fake, but that's not one thing that we can fake. And if you really do have quantitative, calibrated scientific data that shows that happening, you more or less have proved aliens exist.
Could this system detect stealth aircraft in our airspace?
It's hard to say. I mean, we did a study when I was at the National Center for Atmospheric Research. Our weather radars were actually able to see the wakes of aircraft that were stealth aircraft. So we weren't looking at stealth aircraft, but we were trying to see if we could detect the wakes. So, when they say stealth, what they mean is it's hard to see. They don't mean it's impossible to see. And the way radar sensitivity works is the closer an object gets to you, the easier it is to detect. So, if a stealth, let's say UFO or whatever, I don't know. We don't know the answer to this, of course, but this is a pretty sensitive radar. So it might pick up stealth. I don't know.
And one of the advantages to this system, as I understand it, as opposed to an active radar system that has an emitter that spins around, is that this constantly stares at the sky. It's a staring instrument. So it's staring at an entire area for a constant period of time, but it's not like a very narrow band where, like, if you had an active radar emitter that is sweeping around and perhaps during its sweep it misses something that flies by while it's not looking, correct? So that's one of the advantages of the passive system?
That's exactly right. So a normal radar works by transmitting a pulse, but it transmits in a beam, and they call it a pencil beam. So imagine just like a laser beam, but it's not that refined, but it transmits in a particular direction. And then if it bounces off something, it's looking for signals that are bouncing off that thing and where it's pointing. So it's not only transmitting in a, with a high gain in just one direction, but it's also receiving in that same direction. So that means, especially something like a UFO that can instantaneously move from one point to another, if it exists, which I think it does. You could completely evade a radar that's looking for it just because it's just like trying to find it with a telescope that we talked about earlier. It's really hard to find something with a telescope. You need a surveillance system. Well, what this passive radar does, its antennas have a very broad, actually hemispherical reception area. So you're looking at the whole sky at once, and it processes that whole picture up to 15 times a second.
Okay.
So if there's anything in the sky, you'll see it 15 times a second until it's not in your view anymore. And the view, these things can see out 150 kilometers.
Wow.
Something like 100 miles.
And the more sensors that are, like, say, in my neighborhood, let's say there are 20 sensors here in Hollywood, and they're all staring at the same piece of sky. The more sensors that are deployed, even if it's in a relatively tight geographic area, does it increase the resolution of the data at all?
It does. Yep. It's like basically a least squares fit. So if you get more and more overdetermined detections of the same object, it just keeps getting more and more refined where that object is and what its velocity is. And it also makes more and more it impossible for it to be some kind of anomalous thing, like radars have this thing called anomalous propagation. But if you had anomalous propagation for one radar, it's not necessarily going to be the same for another radar. It's looking in a different direction. So, those kind of things are very dependent on your position with respect to the target. And if you had multiple detections of this thing, it'd be really hard to debunk that. It would be really hard to find any other explanation than an object in the sky.
So kind of explanations that you'll hear from debunkers, such as radar, false radar returns, that kind of thing.
Yeah.
This addresses that shortcoming, correct?
Yeah. And I mean, another way it does it is just because even with regular radars, if you're looking at something 100 miles away, that's what you're doing. But this, the idea here is a grid, or, kind of a random grid, right, of 10,000 receivers. That's the goal. And that means that they're all about 20 kilometers away from each other. So no one radar actually even has to look further than, 30 kilometers, let's say. And if there was one object somewhere, you'll get 5 detections of it from 5 different receivers.
Will weather affect the efficacy of the system, like inclement weather?
That's another, by the way, deficiency of optical systems, right? Is that if it's cloudy and, let's say you have an optical system designed for UAP detection on your roof, and you live in the Midwest, where I'm from, well, that means that half of the year you don't see anything, because it gets overcast, in the fall, and then it clears up in the spring. In the meantime, you have a low cloud ceiling and you're looking at nothing. So this, however, goes right through that. Just like when it rains or when it snows or when there's any kind of weather, your FM radio doesn't go out. You still hear it. That's the same thing.
That totally makes sense. And in terms of the size of the object flying around, if it's, say, a silver orb the size of a basketball, 20,000 feet up, as long as it's in the field of view of the sensor, would it detect that?
You said the size of a basketball?
Yeah, something relatively small. Do you think it would detect it?
I actually wrote it down kind of so I wouldn't forget typical kind of things. Let's see, something the size of a basketball, that's about minus 10 dBSM, they call it. So there's a thing called radar cross-section, and you just look at the silhouette of an object and measure that area of the silhouette. That's the radar cross-section, roughly, right? Something that's like a basketball size, you could see this, the theory, because I worked through the theory, and then you have to make your instrument that good. So my instrument is quite not that good yet. But the theory says I could see that at 90 kilometers.
Wow. Okay, so
If it was a tin foil, let's say a reflective
Mhm.
basketball, if it's just a basketball, so it's made of rubber, that changes the game quite a bit because
Right.
it's radar. You need to reflect the signals, and there is some minimal reflection from just objects that aren't air. Uh, but if it's metal, that's where you get the real significant reflections.
Wow. So, and as we know, as you stated earlier, there is a very long history of UAP returning radar reflection. So there's no
Yeah.
reason why this would not detect UAP.
No, I don't see any reason why it wouldn't work. I do think that I mean, this is what Peter Davenport suggested to me. Mitch, you would be proving UAP, or he says UFO like me.
Sure.
You
Yeah.
would be proving UFO twice a week with this thing.
I love it. Absolutely love it. Well, why don't you give us a tour of what you
Oh,
have, what you've developed, and let's see a live demo of this.
well, if you can share my screen, I'll just start up a demo.
Okay. Let's see. There you go.
So right now, it's in the very much an engineering stage right now. So right now, I'm just going to start data collection. Let me just kind of give you an idea of the setup that I have here, so you can see what's involved.
Okay.
I'm grabbing the camera right off my computer, but so I'm just sitting here at this desk. If you can see that, I have this big picture window behind me, and then I have there's a door over here where I can go out to the antennas. They're just a few feet out there.
Okay.
But what I have is this system. This is a multi-channel software-defined radio. I'm only using 2 of the channels
Okay.
with 2 antennas. And it goes into the computer. So, I mean, as far as the hardware is required, it's a computer and then a software-defined radio. And then these the wires lead over here to just goes outside to the 2 antennas. And that system now is collecting the data. It's set up right now to collect the data for 5 minutes because I turned it into a little time-lapse video that just shows you what was detected during those 5 minutes. But right now it's just cranking away at recording the raw data, the raw samples of the RF receive signal. And then I can go outside and show you the antennas and just give you an idea what that's like.
Okay, Mitch. So we've switched to the camera on your phone. Let's take a little field trip and see what the sensor looks like.
Yeah, so I have there's just 2 cables that go to the 2 antennas that are outside. And they're right out this door. I have a little antenna rotator, by the way, that just so I can point the antenna around and get a better fine tuning on it, which is, a manual kind of thing manual kind of thing an engineer would do, but the consumers would never have to do that. And out here I have the 2 antennas. So the one that you're seeing right in front of you is a Yagi, basically a TV antenna. And I have that pointed essentially at where roughly Denver International Airport would be.
Okay.
And then I mentioned that Lookout Mountain in Golden, Colorado is where the transmitters are, which is pretty much in the direction I'm pointing. And that's why I have this antenna for maximum reception from that angle.
Okay,
so,
the one that's on the one that's on the chair, that's an antenna.
That's an antenna.
Okay.
So it's this metal part is just a frame, but this long tube is the dipole of it. So that's what's receiving the energy. And the way that this kind of antenna works is its maximum lobe is in the direction perpendicular to that dipole. So it's pretty basic how it's set up. The 2 wires just come in into the receiver.
I'm amazed by how compact this whole system is. It's not some huge telescope or huge sled with a whole slew of sensors on it. This is like very, very compact. It's like nothing.
I totally agree. And it's going to be even less when it's, when we package it for consumer use. I mean, as far as the receiver that I was just pointing at in there,
there'll have to be the computer part will have to be with it.
Okay.
But in terms of the antennas, it's going to just be one single mast with one ray on it that does both of these jobs of these two antennas.
Okay, wow, this is fantastic. So let's head back in and we'll continue with the data processing and all of that good stuff. Mm-hmm. So what are we looking at here in this black and white window here?
Hold on a second. I'm just. Well, I told the system to record 107.5, so that's 107.5 megahertz. It brought up the two-channel receiver that I was talking about. So I have a channel A and a channel B, and right now it's just taking that data and cramming it into a file. And there's a file that's getting bigger and bigger. This file for this amount of data is about 1 gigabyte right now. But this is, when we operate the system, that all gets processed so that we don't have to be sending gigabyte files around to make the system work.
Okay. And how long does this particular process take on average for this period of data collection time with processing and everything?
It's 5 minutes or 300 seconds.
Okay. So
that's what I just arbitrarily decided. We can go bigger, but then there would be a 2 gigabyte file if I did 10 minutes,
Right.
So it's just a demo length file.
Got it. Okay. So it's sitting there collecting all of the radar reflections off of anything flying in this vicinity of where you're at.
That's right. There's one antenna is pointed more or less to Denver. So I mentioned before that these are omnidirectional antennas, but for my demo system, it's easier to set it up this way because I need to have 2 different antenna patterns, which I can do with a phased array, but it's harder to do, when I'm doing all this manually for this demo.
Right.
So I'm just using one directive antenna pointing at near Denver International Airport. The other one is just trying to pick up the direct signal from there's a transmitter by Golden, Colorado on a mountain there, and that's where I'm trying to pick up the direct signal.
Now, this obviously, what you've done here takes someone with significant technical knowledge, engineering knowledge, physics knowledge, someone such as yourself that has experience with these types of systems. So for this, in order for like the average person to participate in this process, it needs to make the next jump in development, correct? Into a packageable and deployable retail product.
Yeah, you hit it on the head. And I have to just back up a second too, because I didn't mention the radar is just one part of a 3-pronged system that we want to deploy. So the 3 prongs of the system are the radar receivers, but also a video recording app. So this would be where, a thing where you can point your phone at something you see in the sky, and it would be keeping track of your attitude of the phone, because there's actually an IMU, an inertial measurement unit in the phone that knows where it's pointing. So you can use that to, that data can go back to a central server system. And then if you have multiple people that see the same object in the sky, you can triangulate that and get independent data. But the reason why that's, those kind of apps are out there already. But the reason why it's important in this case is because we have a radar that can see so much further than a phone can see or your eyeball can see. You can't see more than about 10 kilometers an object in the sky before your eyesight's just not good enough, or a phone is not good enough to see that. But this radar can see 100 kilometers away. So what that means is the radar could detect an object coming your way, and this whole system that I described could send an alert to your phone that says, hey, jump out of your chair, run outside and look to the northeast, because there should be an object approaching in 10 seconds. And if you can, get out there, you have a chance of actually getting this independent video data. And even if there was only one person that got a video data of it, so you didn't triangulate it with video data, but you just had a video image, you have provenance, and you also have, you're able to confirm the radar sighting, and it just makes it a multi-sensor event, which is like gold. That's like gold to a researcher, multi-sensor event. The third prong is the National UFO Reporting Center, because you need to call in that you report that you saw that. And, who knows how many people call stuff into, reporting centers around the country or whatever. Who knows how many people do that when there is some other multi-sensor data, but there's no way to connect the two events together. And here we could have radar data, a visual sighting, or some other event. What if a UFO stopped your car? Like we've heard happen in the past before, and you got out and you looked at it and it flew off or whatever, but actually it was also recorded on this system as radar data. I mean, that would be tremendous. And one thing also that we don't correlate is what if somebody experiences an abduction, which we don't know if these are true or not. We just like UFOs, we don't know. But what if somebody experiences an abduction and at the same time there was a radar detection over their house?
Wow.
I mean, these things, that's why these three prongs, putting them together into one system is kind of like the holy grail of proving that UFOs exist. Essentially, also the fact that everybody around the country has access to this information, and people have like a vested interest in it because they've actually were the ones who collected the data because they bought the box, or they're the ones who are part of the video network. All those people are going to know UFOs are real. This would be essentially like, a public disclosure.
Now, let's say I have like the same technical acumen as you do, same educational background, engineering background, and whatnot. With the information that you've shown in terms of the papers, the scientific papers, I could go and make one of these things myself with the data that you've revealed, correct?
Yep.
Wow. Okay. Yeah. I can barely get the lights to work on my show, so I don't know that I'll be able to create anything like that. But the important message here is that you are sharing this with the world and saying, as you're going to prove here in a second, that this stuff does work, and that if people want to develop this, they can do it as well. Or I take it you're looking for investors to help get this over the deployed finish line, as far as taking what is essentially an engineering prototype and putting it into a marketable product, correct?
That's right. I mean, I duplicated Howland's work mostly to prove to myself it worked. I needed to see that. And I also gained the experience that I need to know how this is going to fit into this kind of network I'm talking about. So I gained that knowledge to know that this is something, I proved to myself the proof of principle of this whole concept. But the next step to this is it's definitely engineering, but it's not like research and development. This is not like building something that's never been done before. Really what this is a product development task.
Okay.
And I've been on product development teams, right? And, injection molded plastic and the whole 9 yards, right? And I know what's involved there. It's not a volunteer thing. You can't do it as a member of Galileo Project or a member of SCU, the Scientific Coalition for UAP Study. This is a professional endeavor with professionals who know how to do product development, because and not just that, manufacturing and distribution and support, right? It's the whole thing. The point of it's just like the radar trucks. Great that you have some great radar, but if you don't put it on a truck and go find those tornadoes, it didn't help you. So
right.
An instrument design has everything to do with the whole package. You have to put it all together, or it doesn't matter. So you can have the best passive radar. I could make this thing so great, but if it just sits on my desk giving me great data, I'm never going to see a UFO. The whole point of this is it's got to be taken to a consumer product level and distributed. And part of that is the price has to be low, because people aren't going to pay $20,000 to do this, or $2 million. Right now you can buy a radar like this, but it would cost you $2 million, right?
Okay.
That's not an effective solution for this problem. It needs to be something that's packaged, simple to use, and reliable. And by the way, there's I'm just going to throw this in there. Every time an airplane flies over, it's sending its transponder data, which tells you exactly where it is in space and how fast it's going. And that becomes a calibration for the radar. So every one of these systems that's sitting out there is being constantly calibrated by 50 airplanes at once. So there's no,
Okay.
The reliability of the data is so high due to that kind of calibration. If there's any question about whether this detection is real or not, all you have to do is compare the 20 airplanes that are on the display and see if they're real. So that's part of the system, and that all that stuff is part of this whole system and how it goes together, because it's really a top-down design. How do we prove UFOs exist? Well, we have to measure instantaneous acceleration. Well, how do we do that? Radar is the only way to go. And how do we get radar out there that's going to have the statistics or have a chance of a UFO flying over? We have to have them all over. So you can see how all of this just came out of the same top-down requirement.
And I take it that the transponder data from aircraft or ADS-B data, you could ingest that into the software to subtract those targets out of the visual display, correct? Leaving only the anomalous ones.
That's exactly right.
Okay.
I mean, we can have UFOs that start sending ADS-B data. That's the transponder data, and
Right.
start flying. Flying around, if you call it flying, but start floating around at 500 miles an hour, so they're not detected. But there's nothing you can do about that, right?
Wow. Yes. And are you concerned at all? We know that the Department of Energy has the power to, and we know that the UAP, the crash retrieval stuff, is classified under the Department of Energy under the 1954 Atomic Energy Act. Are you worried that they can use their powers to come and take this away?
That's certainly a concern. And if, given what we said about this system, you can see it's going to give you disclosure. That's
Right.
what it's going to do. So, if they're motivated, of course they could, who knows what can they not do? I have no idea. But what I think is this has to be a project. I talked to SCU about this, and we went through. I worked with Robert Powell. By the way, Robert Powell is the sweetest human being I might have ever met. He's the nicest guy and super good to work with.
Great.
I enjoyed so much working with him, and we put together a plan that would involve SCU, and we presented that to the board of SCU, and they kind of came. Well, we put together a plan that was really, really tailored to both my abilities and my company and what we can do, and tailored to fit us, as well as tailored for SCU. They came back with which, by the way, I didn't mention this yet. It's a $3.5 million project for 24 months. So the idea is we hire the people, we crank away at this, and 24 months later we start selling these units, and then you can buy one off the shelf.
Wow.
So that's the idea of how it would work. SCU came back. They obviously liked the system because they came back with a proposal, but it was more tailored for them more than it was for me, because it was more like 9 years. I estimated it was like a 9-year program, probably $12 million to get all the way to the finish line on it, and several kind of off ramps that seemed to me to be undesirable kind of risks. So but the point of this is something that people recognize would be scientifically really interesting, but it's all got to fit into a practical, doable thing. One of the comments I got from SCU was, "You're not asking for enough money. You can't do it for this amount of money." But I'm pretty good at I have a pretty crack team that can put all this together for that 3.5 million, and that would include the National UFO Reporting Center being upgraded significantly, the app being built, this radar being built. This whole three-pronged system would be put together with that kind of funding.
All right, so you're done recording all the data. Now what is the next step?
Oh, let me, for this demo, the next thing is now there's a file with raw data in it. I'm going to take that file and run it through the post-processing.
Okay.
So let me just click a button here for a second. I don't know if you can see everything, but
I can, yeah.
okay, I misspelled it. Okay, we'll just let that grind away. It takes about 5 minutes to process it.
Okay.
You know, which, in other words, this could be a real-time system just the way it is.
Okay. Wow. So
we're pretty close.
So it's essentially taking the sensor data and turning it into a graphically presentable form. Is that right?
Yeah, I'm going to make what's called an ARD, which is the same display that we saw in the Holland paper, an amplitude range display.
Okay.
So, sorry, amplitude range Doppler display. And then, like I said, well, it's counting percent now, so we can kind of watch that. It's at 20% right now.
Okay. Yeah, I'm not seeing. I think it may be getting chopped off there. So one of the advantages. So you spoke about the fact that the Department of Energy, if they find a technology, a threat to national security, they have the legal means to go and grab that technology and stick it on a shelf so the public never sees it or another company doesn't see it and develop it. But the idea here in revealing this and showing that it works is so that anyone can go and develop it if they have the money, resources, and skill. And since we're really putting this out for the world to see, it's going to be impossible for DOE or the government to shut this thing down.
Yeah, thanks for getting me back on track, because that's why I brought up working with SCU, because the idea was to make this a public, well-known project that we're all working on together, right? And the way the project is designed, there's a bunch of gates that we go through that aren't going to be that threatening to the department. Like, we're going to upgrade the National UFO Reporting Center. We're going to make that video app. We're going to bring some AI capabilities into the National UFO Reporting Center, and we're going to start getting like a small system of the radar working in a local area, right? So none of that's quite a threat yet, but we're getting more and more people involved. There's 300 people in SU. Now, I'm not saying that I'm doing anything with SU. That was a proposal that we went through, and I wasn't ready to accept their counter proposal. But that's the idea. And then, I'll tell you what, Peter Davenport was at the Contact in the Desert, and he was on stage with me presenting this. And the first thing he said to the audience was, "I don't understand why this room isn't full." Because he knows that this is the system that's going to answer this question that we've been asking for 80 years. Are UFOs real? This system will answer that question. Everybody should be really excited about it. And that's the kind of thing we need. That's why I was really excited to talk to you about this, Matt, because more people need to understand how important this is. And we need to get people to start saying, like, if this thing does get shut down, they need to say, wait a minute, why can't I look at radio signals that are coming into my antenna? What's wrong with that? What am I doing wrong? Why is the government preventing me from looking into the sky?
Yeah, absolutely. Well, we know the Pentagon in particular, they are not the most, we'll just say, honest operators there. That's for sure. So back to the cost thing. So you were saying that, like, with Avi Loeb's sensor suite, that was how much per sensor suite?
I mean, I'm just gleaning because I'm in the project, but that was never told to me from within the project. But I saw publicly, it looked to me like about $500,000. About $500,000 per instrument suite, as far as what I kind of gleaned.
And sorry, please go ahead.
Again, like, I think the idea is no citizens touch that. This is something that scientists touch, and this is something that scientists deploy in a few sites here and there. I've heard numbers like 5, I've heard numbers like 10. I've never heard anything like 1,000 or 10,000. There's not enough scientists to do that. So it's back to this radar truck problem that I was talking about before. You gotta You got to go where the phenomena is with your instrument in order to pick it up. Otherwise, you might be waiting for 20 years to get an event.
And what would, and I understand this would be just a rough estimate, what is the estimate of what this product would be, the cost be to a consumer?
Yeah, my target, I've been saying, less than $1,000. But I'm trying to target 500. I just don't want to, I like to, overpromise, underpromise and overdeliver. That's what I like to do. So I don't want anybody to say, oh, it's $550. I'm mad at you, but that's what I'm trying to hit, because I think there will be enough. I think there'll be 10,000 customers for that if it was $500.
Absolutely.
Especially when some of them start to detect objects.
Yeah, well, for sure. So obviously this technology works. You're looking at either Avi Loeb and the Galileo project with a $500,000, a $500,000 massive sensor suite, or this, which is open source. It's passive. You don't need an FCC license. It's not like you have a radar emitter. And this mesh network system for $500 to $1,000. I mean, if I were investing money, I would be investing money in your product. That is for sure. It seems pretty basic to me, pretty fundamental.
Yeah, and we're doing it as a nonprofit. So, my company is a for-profit company, but we'll be doing it as a subcontractor to a nonprofit organization, New Fork.
Okay.
So the idea is we're not expecting to become millionaires on that. This is not what it's for. We might even get to the point where we want to sell it for cost, or we might get a donor that allows us to take a break on it. Maybe bring it down to $300 because a donor put money in to pay for that deployment, because we just want it out there and we want the answer to this question given.
Absolutely. Okay, so where are we in terms of the post-processing of the data?
Oh, that's done. I'm showing the video now. While you were talking, I clicked.
Wow. Okay, so explain what we're looking at here.
Yeah, so this is all 5 minutes of the data turned into 8 seconds or something like that. It's 1 frame per second is how I diced it up. But what you're seeing here is this ARD display. The middle line here corresponds to 0 Doppler. In other words, an airplane's not going further away from you or closer to you. It's staying at the same distance from you if you're on this center line here. So that can either happen because you're going slow, or you're going perpendicular to the radar. And then so that on this axis would be that Doppler. So you see everything that's up here, this is positive. The range is increasing, anything up here. So that's why every dot that's up here is going away from you, and every dot down here is coming towards you. So that's how that works.
Okay, so let me see if I'm understanding this correctly. So what we're looking at here, the white dots. So this isn't displaying like latitude, longitude of an object, correct?
No,
this is the raw data. This is the raw data, radar returns. So the in the middle of the screen, and I don't see your cursor here, so I'm trying to just kind of explain it.
Sorry, you should have told me, because I can make it turn on.
Okay, great.
Wait, it's not turning on for me.
Yeah, it may
here
be.
We go.
Maybe
the wrong button.
Okay. Oh, I see it now. Okay. Is it easier? Is it easier
let me
to
repeat that then?
Okay, please go ahead.
Yeah. So what I was saying is the center line. I was over here moving my mouse and nobody could see it. Sorry about that.
That's okay.
What I was saying is this right along this center line here, that corresponds to 0 Doppler, meaning that airplanes aren't going away from you or coming towards you. They're staying at the same delay. And anything above this line is a negative Doppler, which means that the objects are going away from you. So here you can see any object that's up here is going to the right. And then down here, this is where the Doppler increases, which means it's coming towards you. So anything down here, you can see that's all coming this direction. And if something flies over your head, it would switch from positive to negative as it goes over your head.
Now go ahead. Sorry.
Yeah. The other, that's the one dimension. So that's the up and down dimension, is this receding versus processing velocities. And then this other dimension is the delay. So right here, this big kind of white bar that goes up and down, that's zero delay. So that's, ground clutter, cars you can actually see in there, and stuff like that that are at zero range from you. And then to the right is about, let me see, that would be about probably about 70 miles,
Okay.
60 miles. And so, oh, let me do this, Matt, if I could, just for a second.
Let me ask you a question real quick. The thicker, so you see these horizontal lines in that display.
Oh, sorry. I have it covered up. Go ahead.
You see kind of what looks like static, but then you see these heavy white lines floating around. Do those represent aircraft?
Everything here is more than likely an aircraft. I don't think we're probably seeing a UFO right now. So what we're seeing is aircraft.
Okay, got it.
You're not going to see any cars that are at any significant range. And also their velocity is going to be really low compared to airplanes because these airplanes are going 500 miles an hour.
Okay. But what we are looking at is the processed data of radar returns, and that's what these heavy horizontal white lines are representative of.
Well, the horizontal white lines are really undesired, but you can't do anything about it. It's the dots we're talking about. Each dot is an object. When you see this little kind of glitch here where you get a bunch of vertical kind of static you're talking about.
Right.
That's something that's so bright that has reflecting so highly that it's kind of saturating the system. And then you get this kind of bar like that.
Got it. Okay.
Right along that line. So that does happen sometimes. If you have like a light aircraft fly over, you'll get it'll almost blast out the whole thing. I mean, part of this is the system I'm using here is an 8-bit system, literally an 8-bit system. The system we're going to build won't be an 8-bit system, probably 14 or 16-bit system.
But really, just to kind of like put it in sort of layman's terms, this is displaying the raw radar information. So then the next step would be to take this raw data and convert it into a graphical user interface so that it will display the targets over a map.
Yes, and in order to do that, you have to do triangulation, which means you have to have multiple receivers seeing the same object. So
Understood.
when you just have this one receiver, there's no way you can place it in 3D space yet. You're not there yet.
Got it.
But I will say, again, like the system, the program that we've developed has really has no failure point. We get as far as we can get. And if we get to the point where for example, here's a failure point. We don't know how to do triangulation, for example. Oh, how do we do that? We can't figure it out, blah, blah, blah. Something happens. But even if a bunch of people had this data, you could still use this to confirm a UFO by just doing it manually. All the information is here. And if you had multiple, receivers on the same object, you could figure out and work backwards and get the XYZ. So, I really put a lot of effort into the plan to make sure it really has no failure modes. Every step along the way, you get more, and we get closer to UFO validation.
I love it. Are you presenting this? We have the Seoul conference coming up, the scientific Seoul conference. Are you presenting at Seoul?
No, I'm trying to present at Seoul, but I didn't get any reply from them yet. So, I might be just a little bit below their radar, no pun intended, that they don't realize who I am and what I do, because nobody really knows my name at this point in the UFO industry. So
I'm going to fix that. So we're going to take care of that. Okay, great. So how can people find you, and how can people support your work? And more importantly, how can potential investors contribute to get this into a retail product?
That's a great question. So in my mind, I mean, there's definitely some technical tasks that have to be completed. Like the antenna has to be, We have to make a phased array antenna out of that antenna so that there's no user fiddling with it. So there, I'm not trying to minimize. There's definitely, a lot of work that has to go to get it to the finish line. But the real problem is funding. That is the real problem. And I wish I had a master's degree in funding engineering, right? Because that's really what this needs. I've been pitching this for a couple of years now, and my message is more or less this: hey, if you want to solve this problem, come to me, and I have the program to do it, but I need someone to come to me that's ready to pay for it. Is society willing to pay to have this question answered? And it's not $3.5 trillion or $3.5 billion, like a launch of a space shuttle or something like that. It's just $3.5 million.
It's nothing.
And then I think it's kind of a drop in the bucket.
Yeah.
And I have talked to some people, but it's a little hard to. For some reason, either people see that it worked, they get that this would answer the question, or sometimes they don't. And if they don't see that this answers the question, you can't go very far with that.
Right. Well,
but
awesome.
This would answer the question. Yeah.
Yeah. Well, fantastic. Well, Mitch, we are very excited to hear about future developments. My hope is that potential funders will see this, and it clearly works. You've demonstrated it here live on the air that the whole thing works. I mean, if Lockheed Martin deployed this product to detect things, it works. So, folks, if you're looking at if you're a big funder or an investor and you have money to invest, this is exactly where I would put it. This is bang for the buck. This gets this out under the potential threat of DOE shutting it down, and more importantly, it answers the whole UAP question. So I am so excited to hear about this. I certainly hope you will be presenting it, Sol. I'll see what I can do to help that out. And yeah, awesome. Well, Mitch, thank you very much for joining us. We will put your contact information in the YouTube description, and if folks need to find you, why don't you go ahead and just put out there now where they can find your social media, email, etc.
Yeah, there's a link. It's ascendantai.com/skywatch. So I can spell that out for you if you'd like.
Sure.
ASCEND.com/skywatch, SKYWATCH. So on that link, there's an explainer video, which goes through and, compresses everything I just said with Matt in 6 minutes or 8 minutes. And then it also, talks about some of the other things and has some links to other podcasts and whatnot. And then I'm on social media. I'm Reality Seeker, misspelled, so it's SEAKER.
Okay.
But anyway, you can find me there.
Awesome.
And just to quote, I'll end by quoting Peter Davenport. And I credit him with this whole thing. So just so everybody knows, he thought of this in the 90s, and we should have done it back then. I'm telling you. But anyway, he said, let's end the government's monopoly on radar data. That's his catchphrase, and I like it.
I love it. I absolutely love it. All right. Well, Mitch, thank you very much for joining us, and we look forward to having you back on the show with round 2 of the development of this just amazing product.
Thanks so much, Matt.
Awesome.
Pleasure to be here.
Thanks for joining us. Mitch Randall, ladies and gentlemen.